early morning session. Our first speaker is Nixon, also from the Lancaster group. And it's another rigidity talk. Tony, please start.
Thank you, Tibor. So you might have noticed there was just a little confusion. I was trying to use my own laptop because I had some animations, and they don't work on this one, I don't think. So I'm going to get to some slides, it'll be a little bit blank, and I'm just going to skip past it. So slightly less examples than I was expecting. Also ignore the date, I got that wrong. So I want to talk about the rigidity of graphs on expanding spheres, and this is joint work with Bernd Schultz, Shinichi Tanegawa, who are both here, and with Walter Whiteley, who is thousands of miles away, yet his name has been mentioned multiple times during the week, which is sort of standard for rigidity workshops. So the idea, you've heard about rigidity already, we usually think of rigidity in Euclidean space. So it's also quite standard now to think of rigidity in Euclidean space, but all the points restricted so they can only move around on some fixed sphere of some dimension. In this talk, I want to allow the spheres to expand and contract. I mean change their radius, have the radius as a variable that changes, and you need to add enough edges to prevent any change in the radius, as well as to prevent any other sort of motion or deformation among your framework. So there's been several rigidity talks already, but I'm still going to go through a little bit of the background of just rigidity in 2D and 3D, just in case I lose anybody by skipping that. Then I'll tell you about fixed spheres and what happens there. And then our new work on expanding spheres, I'll quickly motivate it. And really, I'll tell you combinatorial characterization when the spheres are low dimensional, so when you have circles and then you have as much expansion in the circles as you want, and two-dimensional spheres with a little bit of expansion. We can also cover and explain why we can't go much further than that at this stage. So framework, as we all know by now, is a combination of a finite, simple, undirected graph and a map P, which assigns positions in some Euclidean space Rd to the vertices, and then edges provide distance constraints between pairs of vertices. And we want to know to the shape that we get, can we continuously deform the shape in a non-trivial way, it's not a translation, not a rotation, and have some interesting change in the distance between some pair of vertices. So if the framework is flexible, if there's a family of continuous functions which act on the vertices, which preserve the edge lengths, the graph structure, and change some distance between some pair of vertices that doesn't define an edge. And then it's rigid if it's not flexible, so there's no possible such family of continuous functions. I'm also going to talk about minimal rigidity. So this is sort of the borderline case where it's rigid, but as soon as you remove any one single edge, it becomes flexible. So it's on the border between the two, and every edge is actually working to keep it rigid. As soon as you get rid of any bit, it starts to move around. Okay, so in general, as you can imagine, you're trying to stop there being any possible family of continuous functions. This is quite hard in general. So we look at generic frameworks, which we've seen again a few times this week. Generic means that the coordinates of the points are algebraically independent over the rationals. So intuition, you can just think of no points lie a coincident or collinear. No, so the affine span of your point set is all of the Euclidean space. There's no horrible geometry going on. And when we have generic frameworks, we can understand rigidity via the rank of a rigidity matrix. So to do this, we set up a rigidity map, which just tells us the lengths of every single edge. And then we differentiate this. We form the Jacobian derivative matrix, which we call the rigidity matrix up to scaling. It has a d tuple of columns for each vertex. So each vertex in Rd has d degrees of freedom. So there are d columns or d variables representing that. And then the rows of the matrix correspond to the edges. These are the constraints fixing distances between pairs of vertices. And so what we would like is that, just to use this matrix as Asimov and Roth did, so we have, for generic, the framework is rigid if and only if this matrix has the maximum possible rank, i.e. you have the number of degrees of freedom minus the trivial motions, which you can never rule out. You have that many constraints, and that they're all independent. So you have this many edges, and the rows corresponding to those edges are all linearly independent. And then for rigidity, maybe you can throw as many extra edges as you like in there after you've achieved that rank. So we have this algebraic characterization that works in arbitrary dimension, and then in what dimensions can we tell you combinatorial things? in 1D, we can tell you that rigidity is very simple. It just corresponds to graph connectivity. In 2D, Lemam proved in the 1970 that you can say, that you can give a characterization of rigidity. So here the rank characterization had dv minus d plus 1 choose 2. If you just plug in d equals 2, this is what you get. E equals 2v minus 3. And we have a corresponding subgraph inequality because we don't want any subset of the rows to be dependent and throw off the count. For example, like this, if we have just these triangles, and this is a rigid thing, but with the same number of edges, if I just take this one and put it over here, then I have the top count e equals 2v minus 3 is satisfied, but the K4 has one too many edges, is clearly dependent, and the 4 cycle has one too few. This bit can clearly move around, regardless of the fact we had extra edges over here. So you have to spread them out nicely throughout your graph. OK, but in 3D, such simple counting doesn't get us any further. So the rank condition said dv minus d plus 1 choose 2, which in 3D would give us 3v minus 6. And here's a graph that satisfies that count, but it's not rigid. So this is known as a double banana because of the shape you can see. And you can imagine that the two banana shapes can rotate freely around this red line. You think of this as a hinge and maybe fix one, and the other one can rotate freely towards it or away from it, changing lots of different distances as it goes. And as Shinichi said back on the first day, we don't really know of a really strongly believed conjecture that combinatorially would characterize rigidity in this context. OK, so inside of R3 or inside of some higher dimensional space, we can then say, let's make a different sort of restriction, like putting points on a sphere, and say, can we say combinatorial things in this sort of case? And try and maybe head in the direction of R3 in this sort of way. So we set this up in d dimensions. So we're always going to have spheres centered in the origin with radius 1. So when d is 1, we just have a circle, x squared plus y squared equals 1. We have the usual two-sphere in R3 on the d-dimensional versions sitting in Rd plus 1. The Rd plus 1 just has, d plus 1 just has to be a higher number than d. If it's massively higher, it doesn't really matter. You're not gaining or losing anything by going up, so we just always put it into Rd plus 1. So now our frameworks are still, it's finite, simple, and directed graphs, and still it's maps now into the underlying space Rd plus 1. And the constraint is that each point lies on the d-dimensional sphere. So for example, for the two-sphere in R3, each point in 3 dimensions has 3 degrees of freedom, and then the constraint it lies in a sphere takes away one of these degrees of freedom. So you're moving back from a 3-dimensional to more of a 2-dimensional setup. So it shouldn't be surprising that this becomes easier for us to understand. And then, so for rigidity flexibility, we have these points on a sphere, and we want them to stay on the sphere at all points in time. So we can set up the usual rigidity map and differentiate, and we get a matrix which has this sort of form. So this Rd plus 1 GP is the usual Euclidean rigidity matrix we had before with E rows, and now it's in d plus 1 dimensions, so d plus 1 columns per vertex. And then we add on mod v additional rows, 1 for each vertex, and the entries in these rows were 0 everywhere except in the d plus 1 columns for the vertex, where your entry is a normal vector to the surface at that point. So it's encoding the condition that infinitesimally the points must move tangent to the sphere, which is the right thing to extend to continuously staying on the sphere at all points in time. It's more this structure that I care about for the particular talk today. So these were already looked at by Saliolio and Whiteley. And in fact, they were looking at them in a more general problem where they were transferring rigidity results among metrics and among geometries, so looking at hyperbolic space, Minkowski space, this sort of thing. And as a byproduct of that, they showed that spherical and Euclidean give you the same answer rigidity-wise. So they tell us that a framework is rigid generically. Generic has a slightly different meaning on the sphere because you always have to, if you're a point on a sphere, you satisfy the polynomial equation defining the sphere, which means you can't be algebraically independent, but there is a natural definition of generic in this context that just means you avoid that polynomial and the ideal generated by that polynomial, but anything else you can't satisfy. So under that generic definition, then your framework is rigid, if and only if you have a rank condition. So now it's the same condition as in Rd rather than Rd plus 1, i.e. dv minus the number of isometries of Rd, except we've added on 1 to the mod v because we have these extra mod v rows for the vertices, and we want them all to be independent of everything else. The reason it's still the number of isometries of Rd rather than Rd plus 1 is that the sphere doesn't admit any translations. It just admits the d plus 1 choose 2 rotations. So the number of trivial motions we have to subtract from the degrees of freedom is less than all of Rd plus 1. And also, you can say that Le Mans theorem holds. You still have the graphs still just need to be equals 2b minus 3 with this inequality. The extra rank all comes from the vertex rows rather than having to need any extra edges in any way. And then as soon as you know all of this for the unit sphere, say, then you can immediately extend it to concentric spheres without any real hard extra work. So you can imagine you can have n different spheres with 1 point on each sphere if you like, or you can have any sort of thing in between that down to them all on one unit sphere. Okay, so now I want to start to talk about letting the spheres expand. And so this is where I wanted to show a little animation, which I don't think is going to work. I'm going to click and hope something happens. No, nothing is going to happen. So the idea is Euclidean and spherical are the same. So a fixed circle is the same as the real line. The real line, I said rigidity was equivalent to graph connectivity. So a connected graph like this path should be rigid on the unit circle. If I now add the extra degree of freedom that the circle can change its radius continuously, then you have to imagine it, but this example was going to show that you can move it around. It's not too hard in this sort of case to imagine that as oops. And now it's disappeared completely. So as the circle shrinks in, if you have 2 points here that are going along a path, as the circle shrinks in, they're going to come closer together. As it expands, they're going to go further apart. There's no edge there, but it's going to change that distance. You can have to imagine that. Oh. Okay, so the video I already knew last night, I wasn't going to be able to show you. If you want to see it, you can go to hoberman.com, and then they have a long list of videos of things like expanding spheres, expanding helicoids. These are pretty massive physical structures they've built that are sort of the size of this building. Structures, sorry, the size of this room, not the building. I've gone a bit too big. On a more small scale, you can buy on Amazon, sort of 20 euros, a toy like this, which is around this sort of size in the small version, and you can expand it up to this sort of size. And what happens is, it's probably too small for you to see, but there is a very small radius sphere in the middle here, and then a bigger radius sphere that's quite far away. And then in the expanded version, you can see there's almost no distance between the two spheres. So the inner one is expanded at a faster rate, and at the outside, they're both almost the same sphere because they're expanding at different rates. And then the more complicated version where it's not just points and edges. These are more complicated shapes, but a similar sort of idea. So these mathematical toys is sort of one of the motivations. I'll tell you another in a couple of slides' time, but first I want to set up some of the formalism of this. So you can imagine if you have two spheres expanding at different rates, and I throw enough edges in so that one of the spheres is fixed and rigidified by the points on it, and then the other one is still varying, and I want to throw more edges in to fix this outer one. I want to make sure I throw them in to actually hit the outer one, not just inside this smaller bit. So the way we model that combinatorially is by colored graphs, where a color is going to correspond to one variable radius. And so if we want to fix the red sphere, we're going to have to add an edge that hits some red vertex in some way, intuitively at least, to finish off to rigidify that part. So we have a function that gives us colors from some set C. If we have k different colors, and it's k-colored graph, and we're going to keep the case, in my pictures, are going to be the black vertices. They're always on a fixed sphere, so it can be the case that every vertex gets a color, but sometimes we're going to leave some vertices uncolored or black, so that they are the ones that lie on a fixed sphere that we don't allow the radius to vary. And so we set up just the formalism of the sphere. So a color C gives us a particular real number for the radius, and then that radius, it's fixed to start with, but it's allowed to vary in our analysis of it. So we start with all these concentric spheres determined by the colors, and then allow these radiuses to be variables and try and understand when combinatorially we can stop those motions as well as stop any other possible motion of the framework. So the framework itself is a combination of a colored graph and a realization into the underlying Euclidean space so that all vertices with a particular color lie on the right sphere. So the natural thing you would want to do. Okay, so I can set up rigidity and continuous families of motions, and a Jacobian derivative matrix from the rigidity map gives us this sort of matrix. And it's the important thing for the talk is just the structure of the matrix. So this left block column is just the fixed sphere matrix. And then we have a quite simple matrix over here with 0 at the top. And we have this VG chi P matrix, just depends on the colors, the colored graph, and has one column for each color. And in the column for red, the entries are non-zero only for the vertices that are colored red, where the entry is some rate of change of the radius. But because the entries are all the same in that column, we can just scale them all and make them all ones. So really, it's a matrix of zeros and ones given by the colors. Okay, so for generic in this context, which again has a sort of very slightly different meaning to what we said for the fixed sphere, but I won't go into it, we can express rigidity in terms of a rank condition on this matrix. So this condition, d plus 1 mod v minus d plus 1 choose 2, is the fixed sphere condition. And then for each color, they have a 1 degree of freedom in the expansion of the sphere, so we should add one additional, so we should add one additional edge, so one for each color. Except it's not quite that. We have to take the minimum of these two terms. The point is that if every vertex has a different color, then we've moved from having this two-dimensional context on fixed spheres in the 2D case. We've added one extra degree of freedom for every single vertex, so each vertex has 3 degrees of freedom. So we've moved back to the 3-dimensional problem, and then the number of things we can't rule out increases from just the rotations to the rotations and translations. So if k is too big, we have to take something that's slightly smaller than k instead, because the kernel of the rigidity matrix gets bigger at those extremes. But otherwise, this is our count. Okay, so this is the second bit of motivation I said. So I want to look at the two extremes of this problem, when there's 0 colors and when there's n colors. So when we have 0 colors, well, this disappears, but you can just think of this as VG chi P as being the 0 matrix. So that's the fixed sphere case, which is equivalent to rigidity in RD. If at the other end of the scale we have 1 color per vertex, then this matrix now has, well, it's got exactly 1 non-zero in each row in each column, and we can permute it to the identity matrix. So the rank of RG chi P depends only on RD plus 1 GP. So we're really just asking to understand rigidity in RD plus 1. So one end we have RD, and the other end RD plus 1. And since we understand rigidity combinatorially in R1 and R2, we'd hope that we could use this to move from R2 towards R3 in some way. Unfortunately, I'm not saying we can do that to any great extent, but that was sort of the motivating idea. Okay, so this is another video that won't play. Well, let me just decide whether it's rigid or flexible. So we have two different spheres, circles in this case, which are both allowed to expand and contract at different rates. So I said we needed one extra edge to a tree to rigidify the expansion of the sphere in the previous one that wasn't playing. So adding this edge means I've got a triangle on that outer circle. So that in theory should have stopped the expansion of the outer circle. And then what we have left is just this path hanging off on the inner one. So in this case, the outer circle is fixed by the triangle, and the inner circle is free to move. So this is still flexible. Down here, we have a slightly different setup. So I've, like I said, the black vertices are on a fixed circle, and the red vertices are on a circle that's expanding at some rate. So again, the triangle is going to fix the outer circle, and now this degree 1 hanging off is okay because there's no expansion in the circle, so this is rigid. And this one is also rigid for similar reasons. This triangle fixes the expansion from the circle for this point, and because it fixes it for this point, it also fixes it for this point. So even though this is degree 1, it's okay because the circle has been fixed by the triangle that went before it. So these are both rigid, and this one appears flexible. If I can, yeah. So flexible and rigid. So even though they all look very similar up to the colors in this extra degree 1. Okay, so as we've heard in a couple of talks this week, to understand necessary combinatorial conditions, you just count degrees of freedom versus constraints. And doing this gives us count here. So it's exactly the count for the rank condition, except n of the rows were coming from the vertices, so I lost n there. Otherwise, it's here with this minimum term. And then because of the interaction of the minus this term and the plus this term, we have to actually put the rank function in here. We can't just put d of mod v of f minus this constant in here. We have to actually put the rank function for the rigidity matroid in dimension d from this. And this gives us a monotone submodular function. And at least in the case when d equals 1, it's positive. So we can use Edmonds' theorem to tell us this gives us a matroid. For d greater than or equal to 2, the minimum bit here can give us make it negative for I think for a single edge, if you pick the right colors. Then, so when we do the d equals 2 result in a couple of minutes, we'll have to say that we actually replace this by something slightly simpler, and hence the restriction on what k we can actually pick and why we can't go all the way to 3D, well, one of the reasons. So here's the first theorem, that when d equals 1, into those necessary counts, I've just plugged d equals 1. The rank function of the rigidity matroid becomes the rank function of the cycle matroid, so that's the number of connected components here. And otherwise it's this, and you can notice that when k is 0, we just reduce to the e equals v minus 1, the count for rigidity on the real line. And when k equals mod v, we reduce down to the Lemang count. So combinatorially, as well as from the matrix, we're interpolating from rigidity in the line to rigidity in the plane. Okay, for 2 colors and dimension 2, or most 2 colors, we can give a similar sort of theorem. But we had to get away from the matroid complication, and I'll show you another complication in a minute. And we do this by removing the minimum term and just putting k, which is valid because we've got k so small. So we don't get the extra problems I was saying from the trivial motions in this case. And here again, this is purely combinatorial. I'll just skip through it quickly. This is the rank function of the 2-dimensional rigidity matroid, which is combinatorial, as I show you briefly on the next slide. And so this gives us our characterization for d equals 2 and at most 2 colors. And after I just quickly say what this is, then I just want to say briefly in the last few minutes, a very brief few words about how the proof of both of these theorems go. It's essentially the same proof in both cases that we do. So I'll say briefly about that. But just firstly, the rank function by a result of Lovász and Jemeny is a combinatorial thing itself. So that was a combinatorial characterization. It said it wasn't a rank of a matrix, a matroid induced by a matrix. Okay, so the proof technique is roughly the one Bernd went through yesterday. We know the necessary conditions. We already talked about that. So it's to see the sufficiency. So you split it into 2 parts. You want to have an understanding of your graphs. An understanding, I mean, a recursive construction that you generate all these graphs from some simple brace graphs by applying local moves that add sort of 1 or 2 vertices at a time and only edit your old graph a little bit. And then after you know that combinatorially, you want to show that these moves as operations on frameworks preserve rigidity by arguing with the rank of the rigidity matrix and maybe some geometric insight. So I'm not actually going to tell you anything about how the combinatorics works or about how the geometry works. I just want to show you what the operations are, essentially. But the other thing I'll mention is that we don't just apply induction on the number of vertices, which is the standard thing. We have to actually apply induction on the number of vertices plus the number of colors. This is a particular complication in this particular trying to apply an inductive construction proof. But again, I don't have time to go into that at all. So I restrict to the d equals 1 case. So imagine we have just 1-dimensional rigidity. Then if you add 1 new vertex to your graph from here to here, then that's 1 degree of freedom, so you need 1 edge, in theory, should rigidify. And if I, for some reason, wanted to subdivide an edge, then adding these two edges instead of this one, and one new degree of freedom minus one constraint plus two should be the right count. Whereas if I'm in 2 dimensions, if I add a new vertex, I need to add 2 constraints to get rid of the 2 degrees of freedom. Or if I subdivide, then I need 1 additional edge as well. So we want to do the d equals 1 case, which then interpolates between R and R2. So we're going to have to use sometimes the R ones and sometimes the R2 ones. And the way we do this is when the colors are nice or not. And nice or not, I mean whether they're color isolated or not. So if the new vertex is uncolored, then we just do this one. If we want to add a degree 1. If it's not color isolated, so there's already a green vertex, then we just do this one. So the idea here is that if it's rigid and has a green vertex, the green circle is already fixed. So when we add a new green vertex, it's on a fixed circle, so it doesn't have the variability of the circle, so it's fine. Whereas if it's color isolated, there's no green vertex, so when we add the green vertex, it has the expansion of the circle to deal with as well, so we need the extra edge. And we have a similar idea up here. We have an uncolored case, a non-color isolated case, and a color isolated case. These 3 different cases for each of the 2 moves. And just to point out that the point where we need to use induction on the number of colors plus the number of vertices comes up in this move. But I'm not saying anything about how that happens, because I've only got 2 minutes left, and I want to explain just briefly why we couldn't do, why the combinatorial counts for the 2-sphere and k equals 3 do not work. So give an example, like the double banana example I showed at the start, why those counts go wrong. They give an example satisfying those counts which are not rigid. So the 2-sphere is like the plane. So my pictures to start with are going to be in the plane. In the plane, if I add a degree 2 vertex, it's got 2 degrees of freedom. I add 2 edges to rigidify generically. And so this is minimally rigid. I do it again, and I do it again. This is all minimally rigid in the plane, so it's minimally rigid on the 2-sphere. So now I think of it as a framework with the black vertices on a fixed sphere, and I'm going to start changing the colors of these 3 guys. So I change the color of the first one to red and allow that to be on a sphere that varies its radius. So I need 1 extra edge. I put the red one in. This is minimally rigid by our theorem. I do it again to the green one. I can't work this thing. I do it again to the green one, and I add 1 extra edge, and this is minimally rigid by our theorem. I do it 1 more time, and add a blue one, and then this satisfies our count condition, but you can see the same continuous motion of the 2 bananas we had earlier keeps the black vertices fixed. These 3, red, blue, and green, all have 3 degrees of freedom, can move independently in R3, and rotate around this hinge by the yellow line. So this is a graph that satisfies the counting condition but is not rigid. And okay, so very quickly, since I'm out of time, the most interesting problem I think is, could you do k equals 3? Because surely these concentric spheres, 2 dimensions with only 3 colors, is surely significantly easier than when there's n colors and you have the full 3D rigidity problem. But it already has this sort of example that's similar. So could characterizing these combinatorial, excluding this, maybe there's just this one bad example, give you some idea of how you might do something in the harder case. The other things briefly mention is the examples you'll see if you go to the Hopeman website mentioned, or the toys you can buy, all have high amounts of symmetry. So it'd be interesting to symmetrize these, as Bernd talked about yesterday, and we actually wrote down necessary combinatorial counts for this case, but we don't have any sufficient characterizations of this. Or Shinichi talked on Monday about global and universal rigidity. So you could ask about these different extensions of rigidity in these contexts. Or you could say, what's special about the sphere as this fixed object in RD+1, and pick your favorite other geometric object, a torus or something else, and ask about, maybe if you pick a weird one, then it's not the radius you want to expand, but some geometric object, and have some extra variation, some way that you can control, and ask similar sorts of questions in that context. Right. Thank you.
Okay, thank you.
That's the only one we know.